Hello everyone, as in our last video we talked about list and certain operations in list. So now we are going to talk about two search algorithms, two very popular search algorithm related to list or array you can say, which are linear search and binary search. We are going to look at these algorithms, how to write these algorithms, and after that their time complexity, and we are also going to take some questions from the lead code to solve these questions. For binary we are going to take a 2D array question, a 2D matrix question, and we are also going to solve that same question using linear search. So first of all, let's take a look at both of them. First of all, we are going to start with linear search. uh, Linear search. So what is linear search? For example, if we say we have a list of any input, here we are taking a list of 1 to 9. If we have to find a particular element from this list, take for example we have to take 6. Our target is 6. We have to find the 6 from this list. So in linear search what we will do, we will iterate this list and one by one and check if our element matches the target element or not. So what we are going to do in linear search, we are going to loop make a loop through list through list, and then we are going to use a if statement to check if our element is matches our target or not. If it does, if a statement comes out as true, then we will return that element, return that index or element as the question asks us to do, and then we will break the loop because we don't need to go any further. If we already got our target, we don't need to proceed any further. If we did, it will just take extra compute power and provide no result at all. So that's all we have to do in a linear search. So, and the time complexity of a linear search will be time complexity will be big of n. What does it means? That if we increase our in like these take n, like here there are 9 numbers, so we will iterate the loop 9 times. So if you increase it to any number like 1000 or 2000, iteration will increase with that in worst case scenario. So linear search is much simpler than any other search algorithm, but it also takes the most time. So now we are going to make a linear search algorithm and see how it works. So let's just comment it out. We are taking this same list. Let's just give it a name num, and we have a target value. We can take our target values as anything. Let's just take 10. 10 does not exist in this list. So we are going to, you can either directly write the code, but I'm going to write it inside a function so we can call it again and again whenever we want. So let me just name it linear. What does linear will take as an input? It will take a list. We are taking m as a list here. What we are going to do now, we are going we have to iterate through every single element. So we have to make a for loop for I in range if you have to return the index of that number, then you can write range. Otherwise, if you have to only check if that number exists or not, then you don't need to write this much. You can only do you can do just num, then just type if I equals to target, then return. You can either see num dot index I, which will return the index of I, but we don't need to do it because we don't want index. We just want to check if that number exists or not. So we are returning 1, or you can return true. If what if value doesn't exist? So if value exists, it will return to true, but if it doesn't, then we have to write a return false. Now by returning false, this function will end in either term. So here we just forgot to give it a target element as well. We have to give it target 2, and here we are only using m. So let's just call this function and check if it exists or not. If this value exists, the output should be true. If not, then false. So let's just see. Our file name is search. And here you can see the output is false. It means there is no value named 10. Let's just do it with 1 again. Now you can see it's true. So now as you can see, this is all you have to write in a linear search algorithm. We are also going to see how you can write a linear search algorithm for a nested list. So now just let's make another variable, and we are going to name it linear 2D for an 2D array. We are taking that list and taking target as t here. So how we can make this loop? Let's just first say take an array, a nested array. So here you can see there is a list which have another list inside of it. So we have to iterate 2 times just to get an output. First we will write for I in M. Then we have to write for J in I. By this we are already when we wrote I in M, we get this thing, and after we used another loop, we will get the number inside of that list. So now we get 1, 2, or 3. Now we have to check for it. If J is equals to T, we will return true. And what if there is no number inside that array that matches our target? Then we will return false. So now if we call the number, and here our target is 1, let's just say run it. Here you can see true, that this number exists inside that list as well. But what will be the time complexity of this function. Here the time complexity will not be big O of n. Here the time complexity will be big big O n square, because if you see we are iterating 2 times. So if the list have uh, three three elements, first we are iterating in each of these 3 lists, then we are iterating uh, in every single list. So instead of, so our iteration bec- becomes double. So here the time complexity will be big of n square. If we need a third loop, for example, take if we have a list such as this one, then we need to add one more loop here, and if we add one more loop, the time complexity will become, instead of square, it will become cube. So just remember this thing, that if the number of loop will directly change your time complexity by a very big margin. So you don't need, so try to minimize the number of loop you will need in a function, because it increase the time complexity very much. Now if we take a look at the graph of time complexity of linear search, then we have things like this. Wait a minute. Here, as you can see here, this is the graph of time complexity of linear search. As you can see, with the increase in the number of elements, the number of comprehensions, or you can say the number of computation loop, increases linearly. So if you give it more elements, it will take more time. And this thing is not realistically usable in real life scenarios, because if we need so much computation power with every single increase in number of element, we have to wait for such a long time, and we can't, in real life scenarios, it is not very usable. Or so we have to come out with a better search algorithm, which is binary search algorithm. So let's just take a look at the binary search algorithm. So here we are done with linear search. Let's just go with binary. So let's just take, let me just remove these print statements so they don't print again and again. We are now taking a look at the binary search algorithm. First of all, the time complexity of this search algorithm is big of log n. Why log n? If you take a look at this graph carefully, as you can easily see this line, and it is not increasing linearly, rather than it is increasing in a linear function with the increase in number of elements. So how we can write a linear search algorithm? To understand linear search algorithm, you have to understand a very basic thing. Plus, with the binary search algorithm, you have a certain condition which is needed to be followed. The condition is list have to be sorted before applying algorithm. And why it have to be sorted? Because we are just going to see why. In linear search, it doesn't matter. It will still work even if list is unsorted or in any order. But binary search need the list to be in a specific order, either ascending or descending. But how we can? But the question is, why the binary search algorithm need the list to be in a certain order? We will see it by taking an example. For example, think you have numbers from 1 to 10, and now this is, you have to guess which number is our target. For example, we are supposing that our target is 9, and ask you to guess which number is our target. Either you can go linearly by, first you will say 1, I will say no, that's not the target. Then you two will say 2, I will still say that's not our target value. You will say 3, 4, 5, 6, 7, 8, and 9. On the ninth try, I will say yes, this is the target value. This is how we will go in a linear search. But here we are not using a linear search. Instead of a linear search, we are using a binary search. So in binary search, how we are going to compute this thing? Here, I will first say, if I ask you guess our target value, you will guess value such in the middle of this number, in the middle of this array. For example, you said 5. You said 5. I will say the guess is wrong, and the value you said is less than our target value. So 5 is less than 9. So what it means, all the values before 5 are irrelevant now, and you don't need those values. So you don't need 4, 3, 2, and 1. So you don't have to look at these 5 values anymore. Now we only have to work with these 5 values. Now you will take, I again ask you to now guess what is the target value. So you will again guess the middle value, such as you said 8 this time, and I again said no, your guess is wrong, and the value you guessed is less than our target value. So now 8 is less than our target value. So now only two values are there, which is 9 and 10. Now I ask you again, guess which value is right, which value is our target value. You said 9, and this time I will say yes, your guess is right. How many guesses you need? It is 3. You get the value in 3 guesses. But imagine if you are using a linear search, you need 9 guesses. Here you did in 3 in binary, but 9 in linear search. Just see how much big of a difference is there in 3 guesses and 9 guesses. So every single guess is take computing power, and every single code takes memory as well. So what you think, which is the better one for our use? It's the binary one. But just remember this condition, which is have to be fulfilled before using this search algorithm. So now we are going to see how we can write this code. First, we will write it for a 1D array or list. Let's just take our list as m and target value. Now how we will start writing it? So as I told you, we will take a value. Let's get it with a list. You will guess the middle value, but how you will find the middle value of a list? To find a middle value, the best thing is if you know the first value, if index of first value, index of last value, then just you can easily get the middle value index by adding those both values and then dividing them by 2. So let's just get the first index, which is 0. This is the leftmost index, and now we are going for rightmost index. To get the rightmost index, you can easily say the length of list minus 1. We have already talked about it to get about it, that if you subtract and then minus 1 from the length of an array, you will get the index of last value. Now we will use a while condition. What does it mean? It means that if while condition will work when value of low, which is our rightmost index, is less than our the value of our leftmost index is smaller than or equal to our rightmost index value, which have to be true because you won't change the direction. You can't say this will become our rightmost index and this will become our leftmost index in any certain case. Now we have to find the middle value. To find middle value, we are going mid, low, which is, and then high. Then divide the sum by 2. So we already got this the index value for this middle element. Now we have to compare it with the with our target value. So we will write if m mid equals to our target value, we will return true that this element exists inside this loop. But what if, as we talked, the value can our mid value can value on this middle index can be smaller or greater than our target. So if this value is smaller than our target, what does it means? Like here we talked about 9 and 5. 5 is less than 9. So now you can say we don't need these values before 5, we only need values after 5. So you can say 6 will become our leftmost index and 10 will be our rightmost index. So we will change our rightmost index by 6. So we will set and what is our leftmost index? That is low. So we will change low to mid plus 1. We are skipping mid as well because we don't need to include it because we already know it's less than our target value. Then what if the value is greater than? So we are writing else. What if the value is greater than? For example, you guessed 5, but the original target value was 3. So you don't need 5 or any other value after that. So you will change your rightmost index to the value before the middle index. So now we will write high equals to mid plus minus 1, sorry. If the function returns nothing, then what we will return? There is no need to worry about that. The what will return? So we will do what we will do. We can also take like found equals to 1. Found equals, let's just take it, found equals to false. If we found our element, we will change found into true and then break the loop. So here we are done, or you can just simply write a return false statement outside the while loop. Let's just do that. We will write let's just return false and let's just see if it works. Let's just call it. We already have an array of num. Print binary num 5. If 5 exists in this list, then our output should be true. Here if you see it's true, let's just change the number and see if it works for other input or not. Here you can see false. So our binary search algorithm is working perfectly. Now we, as we said, we will talk about some we also do some search question on a 2D on a 2D list or a nested list. So let's just see how it works. So first of all, we already talked about a 2D search with linear search. Now we will talk about a 2D list with binary search in it. So if let me just declare the function. So while writing this search loop, you can do either two things. First of all, you can use two binary searches, or you can write uh, one binary search or a linear search inside of it. It totally depends on you how you want to approach. If you want you don't want some complexity, you can either use a linear search. First of all, we are going to see using a linear search with inside of a binary search. So let me just copy paste it, because most of the content will be same. So now, yep, now we already got our high and low, our mid value as well. If and we are searching for m mid, but here m mid is a list itself. So how we can describe it? So let's just check. As we already talked about, all the lists have to be sorted either in ascending or descending. We are taking as listed as sorted in ascending order. Let's just take an example of 1 comma 2 comma list 3 comma 4. Think our mid index return us this list. So if the last element is less than our target list, then we don't need this list. If our first element is greater than our target list, then we don't need any list before this middle list. So we will continue like this. So first of all, let me just, now we will have to check if this last element is smaller than or not. If it's smaller, -1. If it's smaller than target, we don't need it in any other list. So we will increase our low by 1 plus mid. And now we have to check for this thing. Does the mid index list hold that value or not? So what you can do, you can either call linear from here and just give it target t. So if it will return false, this statement will not execute and you will not get anything in return. So let's just see if it works or not. One more thing, 5 comma 6, another loop, name L equals to that list, binary 2D L and 5. Let's just see if it works or it shows us some problem. Mid, list index out of range. We did everything. M mid is out of range here, so let's just see what's wrong here. For a moment, M mid will give us the list we need, such as this one, and it says this list is out of range. In linear function, let's go in linear. M in target, we are getting M in target. For I in M, so I don't think there should be a problem, but let's just change this thing a little bit and to use it in. And we will, let's just change it a little bit, and we will do so if linear is not working, let's just remove it, and we will make this code again to see if it works or not. We can say M mid 0 is, if this value is in between these two or equals to, then we will return true. Let's just see if it works. It again says mid is out of range. So we will came back at this thing in a while. Let's first look at the time complexity by time complexity of binary search. As we already saw here, as you can see, here is the binary search and here is the time complexity of it. As you can see, there is a very large difference between these two lines, which will represent our time differences. This time difference is enough to switch from one search algorithm to another, which will help us reduce the burden on our hardware. Plus, if efficient, and efficiency is the main thing that drives a company. So binary search algorithm becomes a much better choice in terms of search algorithm instead of linear search. So here we are done with both of our search algorithms, and we will take a look at some questions of these in some time. So